Hello, students. This is the last part of chapter 2, and we're going to go into acids, the factors affecting stability, and the most important thing for you to pay attention to is what stabilizes the conjugate base. That'll answer all of the questions. So we're going to talk about specific effects. There are 5 at the end. Make sure you review the summary on those. First of all, let's ask ourselves what makes an acid stronger than another. So say you have HA, it can break apart, deprotonate, give you the proton and its conjugate base. The stronger acid is the one with the more stable conjugate base. Why is that? You could just believe me, but let me just tell you where that comes from. To answer that, we have to look at an energy diagram. If you want, you could pause and think about that and try to draw one out yourself. Here's an example. What we're going to do is look at the difference between, say, an alcohol with the OH versus a carboxylic acid, which has the carbonyl, the CO double bond, and an OH. They don't have roughly the same starting point, but close enough. But the biggest point is when you have the alkoxide, which is the O minus, that's not resonance stabilized. So that's higher in energy. So if we drew an energy diagram and I have my alcohol in this upper green color, I have to climb a big hill to break that OH bond and give me my alkoxide or O minus conjugate base. However, with the carboxylic acid, such as formic acid, acetic acid, I can break that OH bond with more ease. It's a lower hill because my carboxylate anion, the CO double bond O minus, is lower in energy because it's resonance stabilized. So the key takeaway here is, 1, if your product or intermediate is lower in energy, there's a lower hill to climb. You need less energy to go up this hill. It'll be easier to occur than the one that requires a high hill. So this ends up more easily giving up its H plus. It'll be the stronger acid versus the alcohol. Let's look at a couple factors affecting acidity. The first one involves hydrocarbons. So just compounds with C's and H's. We have one with a triple bond, double, and single bond. I'm going to give you the pKa's. You guys, just looking at the pKa's, you tell me which is the most acidic and which is the least acidic. So the most acidic is the one with a lower pKa. You could just determine that from the numbers. The higher the pKa, it wants to hold on to its H, it's least acidic. So why is that? What's the biggest difference? Just the double bonds, right? What is double bond related to? Multiple bonds are related to hybridization. So in this area, you need to think about sp versus sp2, sp3. Acidity, when we're looking at acids that have the negative charge on the carbon, so if I give up this H plus, the C minus results. When the negative charge is on carbon, you have carbons of different hybridization, and we find that the one that is sp hybridized is more acidic than the sp2, sp3. The reason? Look at the conjugate base. The minus charge is on an sp carbon versus this sp2, sp3. The one where the negative charge is on the one with the most S character, that is more stable. The reason is, remember the shapes of the S and Ps. The S is spherical, so that negative electron density can get closer to the more positively charged nucleus, and that will lower the energy of the system, making it more stable. So then now think back to the energy diagram. It's more stable, lower in energy. It's a lower hill to deprotonate that. Okay, the second factor. Look at this trend. As you go across the periodic table, CH4, NH3, you have water, HF. pKa decreases Number one, what is that trend? And number two, why? So first of all, we go from something really with a high pKa to something very low. The lower the pKa, the more acidic. So HF is much more acidic than methane. So that's the trend going across a periodic table. But why? What's the biggest difference? The main thing that explains that is electronegativity. The more electronegative, the more it can stabilize the negative charge. Because remember what electronegativity is, the propensity for an atom to draw electrons closer to it or more negative charge. That's more stabilizing. Now let's go down the periodic table. If you look at the halogens, you can see that as you go down the periodic table, you actually get more acidic. Why is that? That cannot be explained with electronegativity because you get less electronegative. So what happens as you go down the periodic table? Remember in the beginning when we were looking at filling up orbitals or the orbital shells? You get bigger and bigger as you add more electrons. So these guys are really, really large as you go down to iodine versus fluorine. That's the smallest, one of the smallest. In group 6, you could go O to S. In both of these, we see that you become more acidic. pK of 14 in water versus pK of 7 in H2S. Very similar bonding, but sulfur is bigger. So what explains the increase in acidity? Larger atoms can delocalize or spread out that negative charge better. That's better because the burden isn't all localized and tight. You don't have this negative charge in this little teeny tiny packet, but it's more spread out. There's more space for that negative charge to kind of diffuse into. Okay, a third factor, resonance. Resonance structures we know stabilize the conjugate base because you again delocalize or spread out the negative charge throughout the molecule. So if you have an acid whose conjugate base is stabilized by resonance, and this is the example I gave with the energy diagram, for example, an alcohol going to an alkoxide or methoxide in this case, versus something that's resonance stabilized. Resonance stabilization lowers the energy, makes that hill smaller to climb, so it's more stable, it's easier to deprotonate. This here, the acetate, is more stable than the methoxide, so the corresponding acid or acetic acid is more acidic. It has a pK of 4 versus 15, so that's a really, really strong effect. And this last factor, I just want you to look at these and just intuitively, which one would you think would be more acidic? Fluoroacetic acid or acetic acid? So they both have the same negative charge will land on the O if you deprotonate this H, so you can't explain anything by this electronegativity of where the negative charge is. Both have the same resonance. So the only difference is this fluorine off of here. What can that fluorine do? What do we know about fluorine? Fluorine's quite electronegative, so it likes to do what? It likes to pull electron density. So it can effectively spread out the negative charge. So if you have some sort of electronegative atom or some sort of electron withdrawing group, such as a nitro group, NO2 or CN, these like to withdraw electron density, that can stabilize the conjugate base because it spreads out the negative charge. I can draw a dipole from the C to F here, and it pulls negative charge throughout this molecule, spreading out. And essentially what happens is that burden of the negative charge doesn't just reside on the O's or throughout here, but it could be shared. It's almost like if one family member has a problem and you can share it and the other family members can help, then that burden is relieved or spread out or shared by the other people. So the effect is also additive. If I have 3 fluorines, that will make that even more acidic. The effect diminishes if the fluorine is like several carbons away though. So overall, you can see the effect, fluoroacetic acid, the corresponding acid with the H attached has a pK of 2.7, and acetic acid with the H attached has a pK of 4, showing that the effect here, which we call the inductive effect, that's a really key buzzword, is going to effectively make that a stronger acid. Okay, so this is just a summary. You could read that of those effects. And then the last thing I wanted to just show you is this slide, just a recap of just some polar and negative ends of certain molecules, how they attract each other due to electrostatic attraction. That gives rise to dispersion forces, dipole-dipole forces, hydrogen bond force. If you need a review, I'm going to leave this here. But this helps explain reactivity, why certain molecules are attracted to others. It'll be important when we discuss solvent effects in organic reactions later. And for your information, it also explains why some molecules are solids, liquids, and gases. Okay, that ends chapter 2.